Pleased to know we are on to the final stretch of today's lecture on explainable AI, after which there will be some time to do an exercise and also to potentially return to your neural networks exercise from earlier if you didn't have time to finish playing around with training that. So also just wanted to kind of come back and summarize and clarify where we're at with this so far. I think what I want you to take away from this session isn't necessarily a deep understanding of exactly the full details of every single one of these plots at the moment. I think you'll find that when you start working with them and trying to understand them in the context of your own data, they will start to make more sense. And it will be worth at that point you going back to the documentation for each of these kind of plots that we've talked about to really try and understand how to interpret them in the context of your own data. I want you to go away from today just sort of knowing what explainable AI techniques are available to you, what we can work out with the techniques that are currently out there, what we can't really say, and some of the limitations and some of the possibilities. So I think with all that said, as well, I've gone for explaining a lot of these in the context of classification models, because that is probably what most of you want to create. Those models that say, does this person have a disease? Does it not? That sort of thing. That does make a lot of these plots a little bit harder to understand because we get into that whole realm of probability, odds, etc. And what the scale of each plot is a little bit different. And that's really hard to keep track of. So with all that said, don't worry if not all of these plots are making perfect sense right now. There will be time to go away and play around with them. And I think also just go away and think about what you might want to explain to people and spend time with your plots, understanding them, looking up details, looking up at some of the additional links I provide, just to try and give yourself the best chance of explaining these plots to people. With all that said, hopefully you will quite like the SHAP plots that we are going to go on to in a minute. I'm going to do a little bit of talking about the fundamental, the theory behind SHAP and the SHAP library and what these values are. But again, don't worry too much if you don't understand exactly what these values are and how they're calculated. Again, we will talk about them in the context of how to understand your model. But what these plots are the ones that we showed right at the beginning, the really nice ones that help you to look at the high level importance of your features and also the individual predictions that we haven't been able to look at so far. So actually looking at individual Mr. Smith, who was on the Titanic, and going, right, why did my model predict that Mr. Smith was not going to survive? Oh, it's because he was male and he was this age and this was his passenger class. That's what contributed to this prediction, and this is what of those features contributed the most, and so on and so forth. So that is where these SHAP plots will start to really shine. And the good news is the plot code is quite simple. So let's kick off. Let's get on to the last of this session. Like I say, the SHAP library gives us a range of nice, clear plots for dealing with both global and local feature importance. This one on the top right here looks a little bit like the plots that we saw for our mean decrease in importance and our permutation feature importance. Mean decrease in impurity and our permutation feature importance, just having a nice bar plot showing the magnitude of the impact of each feature. So again, we've looked at an XGBoost model in this particular instance for the Titanic, and we're seeing that being male has the strongest, it's what the model is basing its predictions on most. The passenger class is important, the fare is important, the age is important, and all of the other features have some impact but are less important to your average prediction within the model. We then have these plots over here called B-swarm plots, which help you to start understanding the magnitude of impact of across a range of different individual predictions, each dot being one individual in the data here. We'll talk more about these B-swarm plots in a minute, but just to give you an overview, we can start to understand, does being male have, what does being male decrease or increase your likelihood of survival? And does it always decrease it by the same amount, or does it have less impact on some people? Is the impact very pronounced in some individuals, but for most people it doesn't make much impact, and so on and so forth. More detail about the global action of this model than the bar plot alone can give you. And then we have these waterfall plots. Again, we will go through this in more detail, but it starts to tell you for each individual, how did we get, in this case, to a very low probability of survival, very low log odds of survival. So we're getting back into the realm of log odds here again. But how did we get to this very low log odds of survival for this individual? Well, it's because they were male, this was their fare value, they were relatively young, they were in the lowest passenger class, and so on and so forth. So we can start to understand, compared to our average individual in the model, why did this person have a really low chance of survival as predicted by the model? So Shapley values, they're part of something called coalitional game theory. It's an area of mathematics that is looked at if you have a coalition, so a group that generates a value, how can we fairly distribute the created value between everyone who contributed? Now, this isn't always simple because of interactions. So let's imagine you go out for a meal. Everyone has their own food that contributes to the total bill. That's nice and easy. You can split up that bill without too much difficulty, right? But I only actually had that starter because you were going to share one. You asked for someone to share it with you, and I only stayed for that extra drink because someone else was there. So actually, it's not always just as clear cut as this was my amount. This is what I chose to have. Take this a little bit further, start to think about something like people working together on a machine learning competition. Let's imagine we've got a group of friends who are working together on a Kaggle competition. They've done really well. Their model was really effective. They won a prize of £3,000. Now, all of these people didn't contribute the same amount to the work that was done to get this prize. However, without each of their contributions, their ranking overall would have been lower and they would have won less. So how can we make a fair split across all of these people? It's not just as simple as saying you did this much, you did this much. Now, Shapley values allows us to take the contributions of individuals. So we've got individual 1 here, individual 2 in the dark blue, individual 3 in the purple, and individual 4 in the green. And we can start to take the members of this coalition and look at how they build up to produce a value across all of them. If we want to find the contribution of player 1, we need to start looking at the value, the payout. Let's assume our Kaggle machine learning competition prize of £3,000. What did we get in the coalitions both with and without those individuals? We're going to look at the respective values of what was achieved with these two theoretical coalitions and compare the difference between them, the size of the output, the payout. Now, the difference between these two is what's called the marginal contribution of player 1, of member 1 of this group. What we then need to do is go through every possible pair or every possible combination of coalitions. So we've got this coalition here, 1, 2, 3, 4, compared to coalitions 2, 3, 4. We've got what happens if we just have a coalition with person 1 in and a coalition with no one in. What about coalition with 1, 2, 4? And just 2 and 4. So in all of these different combinations where player 1 is included and player 1 is not included. And we start to compare the marginal contribution, the added value between the coalition in which they're included and the coalition in which they are not included. And we'll get a different marginal value in each case. What we then work out is called the mean marginal contribution for that player, and that is their Shapley value. We can do this, we can repeat all these permutations for different people. So we're working out the marginal contribution of person 2, marginal contribution of person 3, and so on and so forth. So the Shapley value is the average amount that player has made to the coalition value, that individual. Now, the SHAP library, the acronym means Shapley Additive Explanations, is just a way of applying this concept to machine learning models. So what it is doing is turning the question from how does an individual member contribute to the coalition's value, the output that they've created, to how does each individual feature contribute to a model's outputs. So the SHAP value for a given feature represents how much of an impact it's making on the model's prediction per instance. We can start to average these to get these global measures of feature importance, those bar plots saying, on average, being male was a very important feature for the predictions that we made. Or we can start to look at the local level, the individual level importance of different features. So the SHAP library, which is what we're going to use today, allows for the calculation of these SHAP values on a range of different model types. It's a model agnostic method. Fundamentally, all the library needs to know is the inputs and the outputs, and it can start to calculate these SHAP values and start to approximate the importance of features at both this global and local level. It can be used on any model type. It doesn't rely on the model architecture, unlike things like the mean decrease in impurity. There are some extra clever things going on behind the scenes to make it faster on things like XGBoost, LightGBM, CatBoost, scikit-learn models, deep learning models. There are all these different ways of calculating, special algorithms that they have implemented to speed up the calculation or approximation of the SHAP values. That's important because with 4 features, there'd be 64 coalitions, different combinations to sample. With 32 machine learning features, there would be 17.1 billion to work out. It's one of these problems, a bit like when we were looking at the geographic optimization stuff, going to take longer than all the computing power we have in the world. So some tricks for working this out, or some clever jiggery pokery to make it possible to calculate this becomes necessary, and the SHAP library has done the hard work there. So I think the way I find it easy to think about is there's some element of holding some values constant while omitting other values to give an idea of their impact. It's a little bit like the feature and permutation feature importance. It's a little bit like the ice plots, where we're starting to see what happens if I change this feature and what impact does that have on the model's predictions. For those of you kind of trying to understand a bit more about exactly what's going on behind the scenes, you repeat all this for all of the different features. The averages are then used to create a linear regression model. The coefficients of the feature are the linear regression, the linear regression equal to the Shapley value. Don't worry about that. You don't need to know that, but some of you may be curious. I would also add at this point that the SHAP library is temperamental. In my experience, it does sometimes have some slightly odd quirks about the outputs. It gives you not so much the outputs are good. You will sometimes find it doesn't give you things in the format you are expecting, and therefore it can be a little bit irritating to work with. All of the examples I've given today and the examples I've given in the notebooks are tested to work. But sometimes you may find that you change the model you're using, for example, you change from an XGBoost to a random forest, and suddenly, even though that in theory this is all model agnostic, it just doesn't quite give you the same output. Something changes, something about the shape of the outputs changes, and some of the plots therefore don't work. So just be aware of that. If you follow the code closely today, it should all work fine. However, when you get to using this on your own models, you may find that you have some odd errors, and I'm very happy to chat to people if you do run into those errors, because they're not always the easiest to troubleshoot. But I've spent a lot of time working with the SHAP library now, and I will probably have seen the error that you come across. So setting up the SHAP explainer. Let's assume we've started out with a fitted XGBoost model. We're going to use XGBoost in all of the examples today, just because it does give a nice consistent output that works as expected most of the time. So we've created a model. It's an XGB classifier. We've imported XGB classifier from the XGBoost library. We've initialized it, set a random state for reproducibility, and we've fitted it to our X-train and our Y-train data. So our model is ready to go. What we then do is import the SHAP library. This should be included if you're using the ML SAMI environment. This is the same one we used last week for the decision trees and random forests and XGBoost. First thing you need to do is create what's called a SHAP explainer object. We grab the SHAP values from this object. So we create an explainer. So this is a SHAP.explainer. We pass in our model and we pass in our training data. We then use this explainer and pass in our testing data and we're going to call this SHAP values. Now, I've used this phrasing because it matches what is used in the documentation. So when you go to the SHAP library documentation, you should find nice, clear, interpretable outputs. You should be able to follow this and use the same sort of code. Now, what this line does here is return an object of type explainer. So what SHAP does is when you create a SHAP explainer, it looks at the kind of model you're passing in and it works out what the best explainer to use is. So when I said that it had some clever tricks for different tree-based models, for deep learning models, that sort of thing, it will automatically choose the best explainer type to use if you ask for SHAP, if you use SHAP.explainer. So here my explainer object is tree explainer behind the scenes. Here I passed in logistic regression model and it created what's called a linear explainer, but my code didn't change, just the type of this object did. Now that's just worth knowing because when you go to different documentation, you will see people talking about initializing a tree explainer, initializing a deep learning explainer. You don't have to do that as long as you're happy for SHAP to make the decision for you. Sometimes you may want to specify a particular explainer for reasons we won't go into today, but it's just worth knowing that you don't have to make that decision. SHAP can make that decision for you. Now, what we're going to use is our explainer. So remember, we've got this here, explainer equals SHAP.explainer model xtrain. And then we do explainer brackets xtest. We pass in our testing data set to create a variable that we're going to call SHAP values. We can then use the output of this object is what's called an explanation object. So we have explainers and we have explanations. Now, an explanation object, which is called SHAP values, we're calling it SHAP values, like I say, because that's how the documentation does it. It's easier if we stay consistent with that. The SHAP explanation object contains 3 attributes: .values, .base values, and .data. You don't need to worry too much about what's in these, but it's just worth knowing that if you do SHAP values.values, you'll get this output. SHAP values.base values, you'll get this output, and SHAP values.data will give you the original data that was fed into your model. It's quite useful because this means that the various plotting libraries, the various plotting functions that we use in a minute, have access to everything that they need. So sometimes we just want to access the SHAP values in particular, and I'm going to save this as SHAP_values_numeric, just because this is something that is quite often useful to have access to. We might use it in a couple of different ways. So let's just save this as a variable that we can easily get back to whenever we want it. And we know then that the SHAP values numeric is containing these SHAP values, these marginal contributions of each feature for each individual as a NumPy array. Now, sometimes, and this is where I was talking about SHAP not being entirely consistent, sometimes we look at our output and it's not an explanation object. Regardless of why, because I don't know why that is, regardless of why, we can create it ourselves. So what it is worth doing when you have created this explainer, so you've created your explainer, you've created your SHAP values object, look at what is in there. Look at SHAP values, create this variable, and then just take a look at the shape of it. If you don't see .values, .base values, and .data, then SHAP has done its own little thing and decided to give you the wrong kind of output. We can create the explanation object ourselves. We need to do this because otherwise when we try and plot the SHAP values, when we try and plot those nice waterfall and bar and bee swarm plots that I showed at the beginning of this section, it will tell us that it's not in the format it's expecting. Most of the time, it will create an explainer object correctly and you won't have this problem. But some of the time it won't, and it's worth knowing how to create it yourself so that you are prepared when this happens. So we create a SHAP explanation object, we pass in our values, we pass in what's called our expected values from our explainer, our data values, and what our column names are. Don't worry too much about this. You can just reuse this code snippet. All you need to know is that your SHAP values object shouldn't just be an array. It should be something that shows dot values, dot base values, and dot data. So SHAP values can take a long time to calculate if you have a very large number of samples or features. So what we need to do is potentially approximate them by using only a small subsample of rows. So if your training data is absolutely massive, you may find that it takes a very long time, and we're talking, hours to days. That won't be a problem with the data sets we're working with today, but if you're working with a data set with millions of rows, it could be an issue. So all we need to do then is create this entirely as before. We create our SHAP explainer, we create our model, we pass in our model, but instead of passing in the whole of XTrain, we pass in a sample here. SHAP has its own sampling feature function that you can use, and we just said we just want 300 rows of XTrain. What we're then going to do is pass in the SHAP value. We're just going to create this next SHAP values object just as before. We just create our explainer and pass in our testing data. So why are we passing XTrain and XTest around, and how do we know which we should be passing where? You'll come across the terms when you're reading about SHAP called foreground and background data. The background data is usually the training data, and this is what we're passing in when we create our SHAP explainer. This is what's used to understand the general patterns in the data set. The foreground data is what you want to interpret. So this is often your testing data. You're often interested in how does the model generalize from this training data to a new set of testing data. If we don't pass in background data, it usually defaults to the data the model was trained on, but it's good to be explicit. And if we don't pass in foreground data, it will default to the background data. So it is worth being clear about what kind of data we want to explain. The data we are asking it to explain, the foreground data, is what will be used for all of the plots. So when we're plotting individuals, for example, we will only have access to the individuals that we passed in as foreground data. That's worth remembering. Let's go through a couple of the different SHAP plots and what each of them means. I'm going to start with the global importance, our bar plots. Now, what you will see at least is the code is lovely. We have this SHAP values object. Remember, this is our explanation object, and all we need to do to now create this plot is shap.plots.bar. So we can get this plot effectively in 3 lines of code. We created our explanation object, we created our SHAP values from our explainer, and then we pass this into shap.plots.bar. So very little code required to make this plot. Now the bar plot, a lot like our previous bar plots of features, is effectively just saying which features influence the predictions most strongly and by how much do they influence them. Once again, it doesn't reflect the direction. They are almost the absolute value, casting your mind all the way back to the logistic regression stuff we looked at. We're looking just at how much did this increase, or how much did this affect the prediction in some way. Doesn't reflect the direction. Now, in a classification model, the units again are going to be back to our good old friends, the log odds. In a regression model, so when we were looking last week at length of stay, for example, the units of this plot would be in the output value. So it would be in length of stay in days, if that's what our predicted value was. It would be in pounds if we were looking at how much people might cost the healthcare system, or trying to predict how much they'd cost the healthcare system. So that's just kind of being aware of what these units are. Again, it's back to log odds at this point. But the thing to be aware of, again, is it's more useful to just kind of think of this primarily as a good way of understanding which feature is having the biggest impact on the prediction. Next, we're going to go on to B-swarm. Now, B-swarm is sort of starting to move toward this local interpretation, but it's primarily a global method. Again, each dot now is a single data point. So one person, this is passenger 1, passenger 2, passenger 3. Let's say, for example, passenger 37. Each single dot is one person. The colors represent the data value. So here, red means it's a high value, blue means it's a low value. How do we interpret that? Well, for male, we know that 1 means the passenger was male. We know that blue, or 0, which is lower than 1, in this case means the passenger was female. What this means over here, looking at our log odds, remember we're back to log odds here, If you were female, on average, you were more likely to survive. This had a positive impact on your log odds of survival. If you were male, you were less likely to survive. Your log odds here are negative. Passenger class, so higher values of passenger class will, which was like third class in this case, for example, were less likely to survive. The lower classes, which in this case was, first class, for example. So it's a bit counterintuitive there. You just have to remind yourself of what the actual values are. Less likely to survive if you were less likely to survive if you were in class 3, more likely to survive if you were in class 1. Fair, we can see that it's quite spread out, and there's not such a clear pattern here. Fair has an impact. We know from this plot here that fair was quite strongly important in predicting the outcome, but we can see that there's not such a clear distinction between people with high and low fairs as before. Age, we can see that mostly we're seeing that high ages, so older people, had a lower chance of survival, lower log odds, but the impact of age was sort of more, low ages were quite protective. You were more likely to survive if you were younger, and so on and so forth. We can start to tease out the impact of each of those. So the width and asymmetry of the plots can give you an idea of just how much impact the feature has. So you can see here that the ones that had less impact, like age imputed, are quite kind of clustered closely around this 0 line of no impact. But the width of them, the male we know had a very strong impact, so it's a bit more spread out. As I say, in a classification model, these units of the x-axis are log odds. In a regression model, the units of these axes would be the number of pounds, length of stay, and so on. Now, waterfall plots, these are where we're starting to get to this individual level importance. Now, there's quite a lot going on here in one of these plots, but once you start to read them a few times, you will start to understand a bit more what's going on. This value down at the bottom, EF of X, is the base value for this cohort. On average, what was in this case, the chance of survival, the log odds of survival for everyone? What we will almost do is read from the bottom up. So there were 15 features that contributed to a very small impact on the log odds of survival. These were our least impactful features, and because they're so lacking in impact, we've just sort of collated them all into one section. Parch gave a negative impact on log odds. So Parch, I can't remember what Parch is actually in this data set.
It's parents and children, sorry.
Parents and children. So in this case, parents and children gave us a negative impact on our log odds. So a value of 0. These values to the left of the feature names are the feature value for this individual that we are looking at. We are looking at one person here and breaking down the impact, how the prediction was made for them. So we're saying that Parch, value of 0 for Parch reduced the log odds of survival. Value of 2 for SIB SP increased the chances of survival. Age imputed decreased the log odds. Embark C decreased the log odds, so on and so forth. So we can then see the more impactful features at the top of the plot. So P class, age, fair, and being male all had quite a strong impact here on decreasing this individual's chance of survival as predicted by the model. Now these up here, F of X, is the final log odds for the individual. So this individual here has a rather low value. They were predicted to be relatively unlikely to survive. Be careful of placing just too much reliance on the exact values here. Again, just try and view it as which features were roughly more impactful, and be aware of the fact that just a very, compared to the other values in your data set, the lower the log odds are here, the less likely in this case the individual was to survive. If it was a value that was above 0 and higher, they would be more likely to survive. The model is predicting they are more likely to survive. So let's look at an example of someone with a high predicted chance of survival. Here again, we're going to read up from the bottom. There was 15 features in the dataset that didn't really have much impact overall, but they had a slight positive contribution to their likelihood of survival. This person was 52, and that did kind of slightly decrease the model's prediction of whether they'd survive or not. but then we go on to their fare, they were in first class and they were female. They've got a value of 0 for male. So this person had quite a high final prediction of whether they would survive. And again, remember, we're starting from this sort of base prediction for the cohort. Again, this has not changed from the previous plot. This will be the same for every waterfall plot you produce from the same data set. This is the final prediction for the individual. And if you were to go through and look at the predictions for individuals and convert those to log odds, that, you know, when we do our predict prob A to get the predicted probability from our model, if we converted those, we would get this value. So how do we plot these? What's the actual code for this? Well, we just pass in SHAP plots waterfall, and then we pass in an index. So it's making a waterfall plot for one individual. The index reflects the row position in our foreground data set. Now, remember we talked about our foreground data set. That's the one it has available for when it's actually making these plots. So when we look at our X test data set, the first row, index position 0, is this one here. They were male, they embarked C is value of 1, they were 28, and they had a passenger class of 3. Now note that their index is 709. That's not what we passed in here. So don't get confused by the actual index of the individuals. Look at their position in X test. Look at where they were in the testing data set, not their index, their actual position in that data set. Just be aware of that when you are trying to find a particular individual to plot. Now, there's a couple of other fancy kind of plots we can look at. These are called force plots. First, because they're a special kind of interactive plot, we just need to run this shap.init.js line. We then create shap.plots.force, and just like before, we're passing in one individual. And all it effectively is a more compact representation of the waterfall plot. So it's showing exactly the same as before, just that these are decreasing the chance of survival, these are increasing the predicted probability of survival, and this was the final log odds. So this could be useful if you want to show lots of individuals, a sample of individuals, all in a fairly compact space. So you can see that this is just exactly the same. We're not getting the level of detail of the exact, provided impact of the SHAP value, the log odds in this case. It's just an easier way to have it all kind of a high level of what was sort of protective almost in this case, what increased their chance of survival, what decreased their chance, all shown together. Scatter plots are another very useful feature of SHAP, and this is kind of almost starting to get back into that realm of where we had ice plots before. So scatter plots help us to understand the impact an individual feature has on the SHAP value. So again, log odds, we're back in again here, across its whole range. So what we can see is being young was generally had quite a protective impact. It was associated with an increase in the log odds of survival. Being quite old generally had a bit of a less protective impact, was more likely to be a decrease in your odds of survival. But you can see this sort of vertical scatter here. So it's not like you get to age 30 and suddenly your value is always going to be, -1 or 0 or something like that. There is this kind of variation across individuals that's coming from other features, other factors that are kind of going on with that particular individual. The closer clustered these are, then the less variation there is, and this this feature maybe is more strongly impactful. We've just got a little histogram behind the scenes here as well, very faint grey, you might not be able to see too well, just showing the variation in age in this case across our data set. And we can also pass in a colour to view the impact of a second feature. So in this case, we've passed in colour as SHAP values. We need to just use this little bit of code here to say, I want all of the rows, but I only want the age column. And in this case, I want all of the rows, but I only want the male column. Now, what this does here is, so now every red plot is a male individual, every blue plot is a female individual, and you can start again, a bit like we did with that coloured ice plot, to start to tease out the impact of the features. We can also pass in continuous features. So here we've got fair. Sorry, that should say fair in that example. But you can, you're not limited to just binary features like in this case male or female, or let's say child and adult, something like that. You can also use a continuous feature as well. But you might want to pass in a binary feature first in this case. So we've got 0, so we've got all the male passengers, sorry, the female passengers over here, male equals 0, and we've got the female here, male over here, male equals 1 in this case, and we've coloured it by the most strongly interacting feature. So SHAP in this case, we can pass in, if we just pass in colour equals SHAP values, rather than specifying a particular column we want to colour by, it looks at what feature it thinks had the most kind of interaction impact. In this case, it's gone right. Passenger class is the one that had the strongest interaction with being male or female, and this does seem to bear out in the coloration we're seeing. If you're male and you're in the lowest class, it had a different impact to if you were female. We're seeing almost reversal of the pattern over here. So what we can also have a quick think about, those are the main kind of plots that you will want to be aware of for SHAP. And like I said, you can see that generally the creation of those plots is not too complex. What matters is the interpretation of them. Like I say, SHAP can also be used for regression, the continuous value predictions. So like we were doing last week with lengths of stay. Main difference to be aware of is the impact this has on the units across all of the graphs. So here we were doing, this is an example with diabetes. And what we were trying to predict was a numeric example, a numeric value that indicates the progress of the disease after 1 year. Higher values indicated that the disease had progressed more, lower values indicated that the disease had not progressed particularly quickly since the person's last checkup. So instead, this time our x-axis is no longer in log odds, it's in the output, it's in the scale of the feature that we're interested in, length of stay, pounds, disease progression, anything like that. And this is also true of the other plot types. So for example, here, the average for the entire cohort of a disease progression measure was 167. And we can see that, a high BMI, higher than average BMI in this cohort was more likely to mean that your disease had progressed further. This particular value for serum triglycerides, again, had a strong impact on this individual being predicted to have a high level of disease progression since they were last seen in the clinic. Taking SHAP even further, we can convert our classification model outputs to probabilities. The creation of the plot is unchanged. All we need to do is change our SHAP.explainer creation to use a model output of probability. Now, it's up to you to decide whether this feels easier for you to interpret, given all the discussion we've had today about log odds and how it might impact your stakeholders' understanding of this as well. But it does make it a little bit easier to understand the waterfall plot, I would say, in particular. So this is now, instead of being in a scale of log odds, it's in a scale of probabilities and change in probability of survival. There's also a couple of other bonus plots that you will find in the SHAP library. There's a violin plot, very much like the bee-swarm plot. We've got the bee-swarm plot over here. The violin plot is effectively just the same thing without the individual dots. Where there's large numbers of individuals, you will just see the dots where you have a couple of trailing individuals off by themselves. You can also split out your bar plots by cohort. So this was that high level feature importance, and we can start to do things like split it out by whether you had males or females, or maybe we could split this out by passenger class and start to see what impact. So we see that there was a stronger impact of passenger class on the model's predictions for female than male passengers, but not much of a difference of the impact of fare or quite as much for age, cabin number, etc., across the different cohorts. Decision plots are a little bit like waterfall plots again, or the force plots. They're in a way for looking at the classifier's action on an individual, so you can start to see the impact, the cumulative impact of different features. You can also plot this for a large number of passengers and start to see how they diverge, or if there are particular instances where a given feature had an unusually large effect on the model's prediction for one or two individuals, but not the easiest plots to interpret overall. Force plots, you can also create these without specifying an individual index, and this almost takes all the force plots for the individuals, turns them on their side, and turns them into this new graph. I personally don't find these very intuitive compared to some of the other plot types, but they are interactive. You can see there's a drop down on the y-axis and a drop down on the x-axis, on the y-axis and the x-axis. So you can start to play around with different combinations of features and scales to understand your model predictions. So you can have a play around with that. Finally, we might want the relative feature importance as a table so we can more easily compare the feature importance as calculated by SHAP with methods like permutation feature importance. So as we said before, it's important to consider, are your different methods of assessing your model explainability giving you wildly different outputs? That might indicate maybe your model's not particularly good, maybe your model isn't particularly stable, or it may just mean you need to dig in a little bit more about what's going on inside your model. So we can compare the outputs in this case from our SHAP. I won't go through the detail of the code here, but to confirm the values have been calculated correctly, we've looked here and gone, right, what are the mean SHAP values? And we compare that with our bar plot to work out that they are in the right order, that they match up with the SHAP outputs. Now, one of the final things to mention, if you look at SHAP code examples on the internet, you may see a range of examples that look very significantly different with how the plots are created. There was a really big change to the library a couple of versions ago to standardize how plots are created. So you can see it's cleaned things up nicely, but you will see a lot of examples using this older plotting method. And that hasn't been entirely phased out, but it may be phased out eventually. So it's better to use this new way of plotting. Now, there's lots of criticisms of SHAP. It's easy to look at all those wonderful plots and go, well, this is all I need. Why would I ever touch anything else? It tells me everything I need to know about my model, but it is just important to not become over-reliant on it. There are criticisms of it, and it's important to consider other methods, particularly things like permutation feature importance and really nice model agnostic methods that you may want to keep in mind as well. And it's very important, as we said right back at the beginning, to not let your own biases, the need that you have to create a story from a model, you don't want to trip into that whole making causal declarations about the impact of a feature when actually it's just that this particular feature is having an impact on this model's prediction. It doesn't necessarily mean that if we change this thing specifically, our performance against this metric is going to get better or worse, or this patient's going to get better or worse. We just need to be careful.